Did we start this live stream or not? Oh, okay, great. All right. Well, for people, that was the Michael Anti introduction here. The introduction of what we are going to do is talk about biomolecular sequence functions, which apparently I don't have code for. But this is going to be This is going to be what do they call it when you write code on paper? Paper coding exercise or something? What do they call that? Yeah. Okay. All right. So Biosequence. Wait a minute. Biosequence. Okay. So Biosequence is something that we've had in 12. When did we introduce it? 12.2, right?
Right.
Okay. So a typical biosequence in the wild would be something like this, and does that. Okay. So now you are proposing a new piece to Biosequence, which is what tentacles hang out of the thing. Is that right?
That's right.
Okay. So go ahead.
Oh, yeah, that will be adding bonds and between the sequences themselves, and also connecting to other sequences as appropriate.
Okay. So I'm just trying to understand. When you define a sequence, there are a series of characters here. These characters have character positions. That's what you're referring to here. Is that correct?
That's right.
Is that even vaguely sensible? I mean, in other words, guys, with respect to molecules, we also have some kind of positional specification of things. Is that correct? Of atoms in our molecule. Yes. So can we give an example of if I take a molecule, for example, here, and I say something like this. What I'm then doing, if I look at the input form of that will reference, yes, that will reference bonds by, in that list, it will reference bonds by their position here. Is that correct? I mean, but it will reference atoms by their position.
Right, it's essentially a graph with indices as the vertices, and everything you see there are the annotations on the vertices and edges. Yeah.
Recording in progress.
But that's not. If I were to actually write down a graph and I were to say graph ABC, and then I were to say here 1 goes to 2, 3 goes to 4, it's going to be just totally confused.
Right.
Oh, it isn't confused. Why isn't that confused? 1 goes to 2. Oh, I see.
3 to 3.
Oh, I see. It is confused. It is confused. Those are disjoint nodes. A, B, and C are disjoint nodes that have nothing to do with the nodes referenced in the edges specification. Correct?
Correct.
Okay, whereas here, you are choosing to reference. So instead, I don't know whether this is supported in graph. It could be. You could imagine an association here, which says 1 goes to O, 2 goes to whatever, 2 goes to O, etc. And that was how you are, what those indices there are referring to. But otherwise, it's just a magic indexing of that first argument that's happening here. Is that correct?
So yes, but I prefer to think of it as it would be a graph where the first element of the first list is annotation 1, comma, atomic symbol goes to O.
I see. Okay. Okay, fine.
I mean, it's the same what graphics complex or mesh region does.
Right, fine. Okay, so the generalization here is that we're burrowing into character strings to do this.
That's right.
And it is the case, is it not, that characters is sort of as if, so for example, if I were to take this and I were to just make that into a single string, okay, you wouldn't expect molecule to work in that case, but you are expecting biosequence to work in that case. Is that correct?
That's right.
Modulated character set.
Right. Well, I was going to bring that up. I mean, so in other words, the decomposition into positions is done by list index of the return of characters. Is that correct?
Yeah.
Okay.
Does that apply when you have like a peptide too? Are you using single letter encodings for everything?
Yeah,
Yes.
we're using single letter encodings for
Single
everything.
letter alphabet.
We might have
That's the
separate.
reason why.
Go ahead, yeah.
That's the reason why we are able to represent the sequences as strings of characters, because we can represent each nucleotide or each amino acid by one letter. Whereas in the molecule case, it is possible for an atom to have a 2-letter or 3-letter symbol.
good
So
point. Yeah.
joining stuff into a string is messier.
Okay. But so, Brian, are you raising that because with some non-standard biology, you might end up with something that wasn't specifiable as a one-character thing?
Yeah, I mean, you can play games with like uppercase, lowercase to get past, 26, but
No, I understand that, but I'm saying, is there a standard thing? If I'm,
it is normal to see it as 3 characters. Is I don't know, in my world, that when people see peptides, they tend to use the 3-character representations because it's tough to memorize 26 encodings.
Right.
They start to get a little odd after a while.
Okay, so the question really here is it the case that Biosequence, if I were to feed it right now, instead of this, I were to feed it, well, if I just do it right here, if I were to feed it characters of that, does it just get confused or does it happily take it?
It will take it. No, it did not.
It gets into undocumented behavior.
Oh, right. Yeah. We come back to this later in this notebook on the left.
Okay, but so if we allowed Biosequence to take a list there, then this can just be a shorthand for that list, much as smiles is a shorthand for molecules, correct?
In which sense would it be shorthand?
Well, in other words, if you just give a string, in other words, there are 2 signatures, a string, which is decomposed using characters, and a list of objects, which are taken one is each sort of successive token to be used.
But currently, it looks like it tries to parse a list of strings as a list of biosequences.
Right.
Which would be another
Each
way to
letter
interpret
is interpreted as a sequence that only has one element.
Okay, well, so that's the problem then. So I mean, in other words, we've got a conflicting. Okay, if we were to support something beyond a string, the question is there another wrapper we could give that would deal with that? Or is it the case that we want a biosequence which is two, so right now, if I say biosequence of a list of things, what is it going to do? A list of non-trivial, pieces, right? Okay, I hate that message, by the way. I hate that message, but we never have those kinds of messages in the system. But whatever, at least it's informative for us, I suppose.
That wrapper, by the way, is what we use at Emerald. So we have a different head for, say, DNA or peptide, and that's how we know it's internal inside it.
Right.
But as Adrian, this is in the notebook on the left, so we should come back to this discussion maybe later.
All right. Okay. So the first thing you're showing here is there is a way of having unfilled tentacles at the end.
No, the point is not the end. The point is the V connection along.
Yeah, okay, fine. I see. So this is saying these are additional bonds that can occur in anywhere. So this means this is a zipper, basically. Is that right?
Right. Yeah, this was one of the things. It's a little bit a non-standard use.
Why? It's a span. Those are 2 spans.
Yes, right.
And so this thing here, that's very weird. That's a backwards span there. I'm a little bit confused about what's happening here. Is this a single zipper or is this multiple zippers?
That's a single zipper.
Okay, let me unzip the zipper. How can I even do an unzipped zipper?
It's equivalent to the form above. So or should be.
There would be intermediate form. The intermediate form would be 2, 3, 4, 5, 6, 18, 17, blah, blah, blah.
17 up to 13, yes.
Because if you look at the string, in one direction you go forward, when you come back, you go backwards.
Yes, I understand. I understand. That's atom. Right. Well, it's not atom. It's whatever residue or whatever they're.
Residue, yes.
Yeah, residue.
The
Monomer.
Okay, I don't object to this. That it seems okay to me.
Are we
mean,
fixed on the phrase hydrogen for the bonds there? That's a little mixed metaphor with what we're doing with molecule.
Oh yeah, that's terrible.
Even if it's the second argument of bond?
Well, in this case, a hydrogen technically, like GC has 3 hydrogen bonds and AT has 2. If you go to so you'd have to reuse hydrogen in a different way on the molecule. So you might call it like Watson-Crick pair or something else like that. It still works as a 1-to-1, but it's not technical, just so it doesn't get confused with a single hydrogen bond.
Yeah.
So hold on. You're saying there are ordinary hydrogen bonds that live in chemistry in general, and these are not they. Is that what you're saying?
Yeah, these are composed of like multiple of they. So like the GC will have 3 hydrogen bonds between the G and the C, that kind of thing.
You would have 2 hydrogen bonds between them. Yes.
So it's not specifically one bond between 2 atoms. It's an edge between 2. So here the vertices are monomers, and so it's a connection.
Well, but there is a notion of hydrogen bonding that will be relevant potentially for molecules as well.
Oh, absolutely.
Right.
Right. That's why just for namespace confusion, you might call it like pairing or Watson-Crick pairing or something rather than
Watson-Crick is a good choice.
Fine. It always makes me. It's always, but when we name things after people I actually know or have known, it's always different from just these things named after 19th century mathematicians and so on.
Well, if you don't want to include names, you could do a hydrogen collection because you have more than one hydrogen bond from a molecule sense.
I think it's better to if that's what they're
base
called,
pair would be a generic name. You'd call it a base pair.
That would be a good name. That's an easier to honestly. That's a better better known name.
And this could also be used for peptides, or this would be just for DNA and RNA?
For peptides, you don't get. Yeah, you get like disulfide bonds, which are different, and those are really 1-to-1. So that's that works in both spaces of molecule and biosequence.
That's actually what I had planned for the peptide version of this. So the disulfide would be the string specified in the second argument of bond.
Yeah, but secondary structures also held together by hydrogen bonds and peptides, both alpha helix and beta sheets.
Yeah, that's another possibility.
But so if we call it something like base pairing or something, a type of bond, what is that bond? It's because the base pair is the base pair, CG or whatever. But this is the bond that bonds together that base pair. Comments. Is that a silly name? Base pairing?
The stack of the 2 or 3 hydrogen bonds between the 2. It's what everyone logically thinks of what's paired with what. Even energetically, it's actually not even the most important thing. The stack between the up and down is what's providing some of the stabilization energy for the whole thing. But everyone still logically thinks of it as like the connection between them.
Fair enough. But then I'm just asking, what should the name be for this type of bond?
Base pair is totally reasonable. Yeah.
Just base pair or base pairing?
Oh.
See, I think it should be base pairing because it is the bond, right? It is not the base pair itself. That's the point I'm making.
Oh, yeah, that's the point.
Base pair sounds good. Base pairing is the specific instance of AU or AT and CG.
So wait a minute. Are you saying base pairing is good? Because I don't like base.
No, I would use base pair because base pairing is
no. It doesn't make sense. It doesn't make sense. The base pair is C and G. It is not the bond that joins C and G. So we could call it base pair bond, I suppose.
What do we do?
We don't use bond on single, double, triple though.
Okay, well, fine, but then. Well, okay, maybe. Okay, Bob, what do you think?
I was going for base pair bond and in the chemistry world, hydrogen bond as well that we don't have yet, but we've been talking about.
Well, so
I see. So you're saying instead of to call it, name it that, and name it hydrogen bond, so we're not calling it, so we don't have the weirdness of having a bond called hydrogen, so to speak.
Yes, that as well.
well, hold
That
on,
as
but
well.
wasn't the issue that
That's
we
more
were just
confusing.
talking about that it's not a single hydrogen bond between these?
No.
No.
Okay.
Bob is saying when we have hydrogen bonds in ordinary molecular chemistry,
I
right?
see.
As
Yeah,
opposed
that's just,
to,
yeah, that's just between two atoms in
Are you
chemistry.
then going to do
Yeah.
single bond, double bond? On
No,
the
it would
covalent
have.
side?
I mean, so it would have to follow like that. It would
right. But so the
just be
issue
hydrogen.
is what we have right now is single and double. Those are the names there, right?
Right.
Yes.
And triple.
Yeah, I was going to say single, double, triple.
Okay, fine. The
In
question
aromatic.
is whether we rename those, whether we say we prefer single bond, double bond, triple bond, or whether we just call those single and double, and then what do we do with these other ones?
Because the outer head is already bond, I think the shorter word is more natural for me.
That makes
Yeah.
more sense to me
All
as
right,
well.
okay. Base
Yeah.
pair and hydrogen then. It's a type of bond.
I still don't know what I mean. What are the situations where it's necessary to specify a second argument in this? So isn't it by biosequence and then a sequence? We know what type of sequence it is, and you're giving a bonds between them. What does having the freedom to specify what type of bond it is? What does that give you?
That'll matter if you do, Hookstein pairing and other more complicated things than classical.
But the
base pairing.
default could perfectly well be a base pair bond between base pairs, for example.
Further down in the
Absolutely.
notebook, John explains that you don't have to specify it. It will do what's natural, and if it can, it will use a generic name. And the main chain also has bonds, as it were, between residues. And
Sure.
I don't recall the name that
Like
he
this.
uses for those.
Phosphodiester is the
Yeah.
Say it again?
term we use.
Yeah.
Phosphodiester bonds,
I see.
what we call the bonds in the primary structure.
Okay, but so what's it going to be called here? That bond, were we to annotate it, which, so you're saying there are implicitly bonds on the backbone,
That's right.
right?
Yes.
Yes.
But which we are not explicitly naming. But were you to put a bond
We-
between 1 and 2,
We
Between-
did. I think it's somewhere down in that notebook. Right,
okay,
John?
but fine. But so if we had a bond between 1 and 2, which we choose to explicitly give, what would it be called?
Phosphodiester is the string we use.
Okay, I don't know how to spell that, but that's fine. I'm sure it'll autocomplete. Okay, fair enough. All right. Okay, so this is just the defaulting of bond types. That's fine. Composite strands. Okay, what is this about? Okay, so we've now dealt with the additional bonds. So just to understand, in a biosequence, this phosphodiester bond thingy is assumed to be the backbone default.
That's
Yes.
right.
Correct.
So one day, if we were to do other heteropolymers or whatever, there might be a different backbone default bond.
Indeed.
So
For
go ahead.
other nucleic acids, the phosphodiester may be replaced by some other connection, like a phosphodiamidate. I think the Emerald people are aware of other possible nucleic acid connections.
Oh, yeah, there's all kinds of fun you can put in there. But the most common one is if you do peptide, you're going to have, peptide bonds between them.
Yes.
So
Simple
ideally,
amides.
we would so when we move farther to have heteropolymers or even larger extended macromolecules, ideally, the monomer themselves would have defined connection points, and there would be some natural bond that forms between two given monomers.
Right, but what we're saying is, what I'm understanding is, the default right now, implicit or perhaps an explicit option, I don't know, is that for this biosequence, that its backbone, if those things are, bases, the backbone is this. If the things are peptides, the backbone is the amino acids, the backbone is this. Is that
That's right.
correct? Okay. And what happens if I mix? I mean, what do I get if I mix a specification of a? I mean, I don't actually know how these work. Oh, I see. I've got to say the thing I've got is RNA, or the thing I've got is a protein. Is that correct?
That's right.
Yes.
Okay, so that defines what the default backbone is. And I see. So in other words, if we were going to put in a wacky custom object that's the the worm that lives on Europa or something that has some some different kind of thing, we would essentially be changing this first argument of biosequence to specify a different kind of heteropolymer. Is that correct?
Right. Yep.
Yes. And that someone would have to specify what kind of default backbone bond that the new heteropolymer should use. It's an intrinsic property of that one.
Sorry, I didn't understand that. Can you say that again?
So in DNA or RNA, we assume that the phosphodiester bond is the main bond used by this. It's an intrinsic property of that type of biosequence. So if someone were to specify some new kind of heteropolymer, he would also have to specify what kind of main backbone to use.
Yes. Let's see. NA on our live stream asks, any chance of using dot kernel notation for DNA sequences? I don't know what that is. Can somebody speak to that?
I know about dot bracket notation, which is a way of specifying these secondary structure bonds. And I have done some, I guess, examples using that. I was maybe planning on doing a WFR around that, but if it's popular, we could certainly include it.
But so this is a smiley-like thing where you have parentheses or something in the string?
Or you have a second string with parentheses and brackets that specify the bonds, and
there's a group at Caltech who has pioneered a lot of that stuff. It's probably just right up on their website. We can go check it.
Okay. Well, all right. But so it's a different way. It's a more Smiles-like way of specifying this kind of secondary structure information. Is that correct?
Mm-hmm.
I think so in the first approximation, yes.
So what's it called? Dot kernel notation?
That's what the person on our live stream says, yes.
Okay. I mean, so we've been looking into a few different linear line notations for this.
Helm is the one thing we've been looking at a few months ago.
Okay, let's move on. Composite strands. Yes, indeed. This was a Caltech lab link being sent. Good. Okay. All right. So I'm curious to pull it up and see what it is.
Mostly Eric Winfrey's group.
Oh, okay.
And there's many more have joined since then, but it's like him and Niles Pierce back in the day.
Okay. Well, I'm glad my random suggestion when he was being a research assistant to me panned out into such a giant.
It's like the basis of my whole thesis, man. Yeah, it's huge.
Okay. Well, good. It's a motivation to suggest more projects to more people, which I do all the time.
Eminence Greece.
What?
Is that the French phrase? In the background behind all these things?
Yes.
Yeah.
Right. I was my French pronunciation would be even worse.
Sorry if I butchered it.
Okay. All right. So I mean, by the way, that does seem like a very relevant thing. So we should look at it.
Yeah,
okay, let's look at composite strands here.
So now we take a few different ones and glue them together linearly. It's still a sequence. That's the main point. We don't do any branching.
Right. But so what is the bond here at this? I don't quite understand.
It's also
still phosphodiester.
Okay, so I don't know how these things bond, but bind. But okay, so you can do that. I mean, can I put a protein here? No, I can't, right?
No,
No.
because it's not. At least there's no one way to connect peptide to a nucleic acid. There's multiple ways, and one would have to specify what kind of attachment is being done to support that.
Okay.
Yeah, you might call that a conjugate at the end of the day.
Nuclear protein, yes.
But I don't understand what this. So the question here is to have this outer wrapper of a composite strand. So right now, the second argument of biosequence tends to be just a string of characters that represent the elements of this heteropolymer thing. Whereas here you're saying it could be whole strands in that second argument. Is that correct?
Yeah,
That's right.
Seems okay to me. I mean, I do kind of wonder what happens if you have a weird branch thing, but maybe this particular backbone doesn't allow branching, presumably.
No, because they come in
No.
linear sequence, it cannot branch.
Yes.
Yeah. Okay. By the way, this is the new biosequence plot.
Made with a prototype of it, yes.
Right. Okay. It has a certain, it could say happy birthday or something. It has a certain appearance. Do we like the general graphic? Has it gone through graphic design?
No.
Okay.
Not yet.
Does anybody want to comment on what roughly it should look like? I mean, is this kind of, I mean, is this roughly right, or is this like not what you would expect to? What would you expect to see if somebody publishes it in their grand paper in Nature? What should it look like?
When secondary structure shows up, those are definitely traditional. I think the different shapes on the backbone, that's something we did at Emerald to distinguish one backbone from another backbone chemistry. But that's less normal than just seeing the bonds. But the general graph, like the one from the top of the page, that's completely normal to see something like that.
Okay.
When we make a Google search secondary structured DNA, you get tons of them.
Okay. All right. Fine. Well,
Yeah.
that's a graphic design discussion. I don't think we have anybody from there in this meeting.
We should note that we get a colorblind friendly color scale, since the colors show something different than the shape, because the shape matches the letter. Or no, excuse me, I'm wrong. But either way, colorblind friendly color scheme would be important.
Okay.
Good.
All right. Self-bonded composite strand.
Now it gets a little bit more interesting with respect to the indexing.
Sure does. So this bond, so this is something where a composite strand says, I'm going to take one index from the first thing and one index from the second thing. Is that right? What if I gave three things in that first element?
Now, if it's a single number in the bond, it's for the whole length of the strand for this strand for these strand indexes.
Oh boy. Okay. So it's a concatenated part number. Really?
Yep.
Right.
Really? Is that really a good idea?
Now, below is the alternative or addition.
I understand. That's a more full form. I mean, are you saying that these are both things that you would recommend using, or are you saying I mean, this one looks to me kind of crazy. This one looks to me unbelievably unmodular. As in, if you say I'm going to add a character here, and it's like boom, something to do with the fifth sequence got misaligned, that doesn't seem like a very good thing, right? I mean, to me,
I was thinking we could support both, but we don't have to support the linear one, the fully linear one.
No, I think we should go with the second one, the modular one. The argument Stephen just made about doing an insertion in one of the segments completely makes everything downstream broken.
Right. I'm just wondering, is there a case in which the composite strand, I mean, this is a question for users of this stuff, in which the composite strand really is thought of as being, sequentially accessed? Or are these different sections going to be ingested by a different part of the animal, so to speak?
They're
Do you
generally
understand my
thought of
thought?
as consistently one thing. Like there
I see.
are concepts of things like gapmers, where literally every other base you'll do like a different backbone chemistry. But you think of it as one sequence at the end of the day that you produce.
What are they used for? These composite sequences? Where do they show up in biology?
Not naturally, but in therapeutics they show up all the time. Like all the new
Yes.
antisense
Antisense
stuff that people are
oligonucleotides,
making.
yes.
Yeah, but
Yeah.
also multi-strand peptides, or proteins that have multiple strands.
You
They're
mean,
not.
mean
They're
they
a
will
composite. They're a composite, but the ends aren't. Well, actually, no. Then they're not a.
You could. So you're saying a protein would logically be like a series of peptides that are broken up? Sometimes people do that.
Yeah,
They'll say this region is this. We call it this region.
Yeah, these in John's nomenclature further down the notebook, they fall under the collection.
Okay, we're clearly the thumb is not
Yeah.
far down, so maybe I should look further down here.
Also, we
So
were thinking on providing machinery to go from one indexing to the other, so that if you really wanted to insert one, you could go to the part one, insert, and go back. Because sometimes this is more convenient, sometimes this.
I understand. Okay, I mean it's horrifying to have functions that do such a conversion, but let's keep looking.
Is the term composite strand fixed too? Because you might call that a chimera, is the sort of natural phrasing people would use for something like that.
Chimeric sounds, yeah.
In this case, it'd be like a DNA RNA chimera, but you might get that in synthetic context too. You'd still call it that.
And does that apply to proteins also?
Probably no, because your backbone chemistry doesn't often change in the peptide world. It's like it's a logical grouping of a region or a group.
Right.
For.
I mean, one thing, if you're not in the field, then composite strand is more. It's more clear to someone who's not in the field what it is. If you're outside the field, then you think it's a mythical beast, right?
And I haven't seen anybody refer to nucleoproteins as chimeras.
We're pretty in the weeds, though. I mean, making chimeras is something that you're already at PhD level stuff.
Right.
You're not going to learn this in Bio 101.
True.
Right.
Your user base is going to know that word for sure.
Well, depends on, okay.
We could accept it and then normalize to something more traditional.
I don't, the thing that bothers me about composite strand is the thing is an end-to-end composite, which is not obvious. I mean, a composite strand could be something that has multiple parallel, to me, not knowing anything. But let's keep going here. I think I consider this okay. I think the chimera thing, what's that?
Mixed strand?
That might be better. I mean, we're making up this term.
Yeah.
For some reason, necklace comes to mind for me, but it's not cyclic.
No, but that gets. I mean, why are we not
terms that get used
calling
like
it chimeric strand? But hybrid? Is that
hybrid? Is
hybrid? Sure.
Hybrid strand sounds very reasonable to me.
And it's shorter.
That doesn't matter. It's all auto-completed anyway. Okay. All right. Let's keep going here. Keeping track of indices can be cumbersome. You don't say. Okay. What are we doing here? Is this whole section about how we deal with the labeling? Oh my gosh. Okay. The
Some
labeling.
Potential conveniences for this bands.
Okay. So the question is there going to be another meeting X amount of time from now where we're talking about tensor networks or something, or neural nets or whatever, where we're going to have the exact same problem of matching things up like this, and where we're going to say, oh, well, if we'd only had, so what is the basic problem here? The basic problem here is you've got some lists and you are trying to pair up elements from different lists. Is that a true statement?
That's right.
Yeah, I think that's characterized it pretty well.
Okay, so what will be the general way that we would think about doing that? So we've got two lists, and they're A, B, C, D, E, and another list is of a different length, X, Y, Z, W, for example. Okay. Now, what are you trying to do here? You're trying to say what pairs with what, right?
I mean, the trivial one would be just list them, but assume basically that both lists are long and you have long contiguous strands with a pattern.
Right, I understand. So the question then is, what are some typical things you might want to do? You might want to, for example, you might want, I don't even know, you might want the beginning of this paired with the reverse of this or something.
Exactly.
Yeah.
Yes.
So the issue then is, okay, so it's a question of, and you've got a whole bunch of wacky forwards, backwards, whatever things to specify that, which may be the only option. I mean, I don't know.
I mean, this is more or less brainstorming. This is not obviously the final version.
Okay, but then, so what we've got normally for indexing into a list, we've got lists of parts, we've got spans,
We have in some sense band, but it's slightly different word.
That's for multidimensional, right?
Yeah.
Except the band,
For arrays.
I mean, doesn't band, right. But I mean, in a sense, okay. So again, we've got a matching of spans, right? That's the typical case.
Yep.
Am I right?
Okay.
Yep.
Yes.
So it's, what the heck is this thing here? So what is this?
Strand 2.
Oh, I see.
Second piece of the compound one.
I see. That span is being mapped onto. So what happens if these spans are of different lengths?
Then you can't map.
What do you get? An error message?
Yeah, the only realistic chance.
Well, the molecule self-destructs. Okay, so those spans, any two spans that are mapped onto each other have to be, okay.
But you could have, say, in the second one, a twice as long list and then have in the last argument -2.
Fine. Okay, so but these are extract specs. Is that a correct statement? These lists here, that's not a list. You have a typo there. But this list is an extract spec. Is that true? If I say this.
No, I don't think so, because is it? We extract honor the order.
Which order?
Going backwards.
So second components are going from first to last in steps of 1, paired with the fourth component going from last to first in steps of -1.
No, I understand that, but I'm asking if we were, look, the way to think about this is the following. Whatever the identifier is, okay, so here's a concept that basically what Bond is doing is it's taking some indices I1, I2, blah, 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 that Bond is fundamentally going to do this. It's fundamentally going to have, etc., comma, J1, etc., J2, etc. And okay, and that then, actually, there's two ways to think about this. Okay, a better way to think about this will be in terms of the transpose, because in the transpose, you're guaranteed you'll never have hanging things in it. In other words, that the final canonical form that you're trying to achieve is a sequence of I sub n's, J sub n's. Does that make sense? So in other words,
always a list of pairs.
Yeah, right. So the bond, the generic bond, the simplest version of the bond is just, so this is essentially a listable bond. So an ordinary bond will be, which is presumably, I mean, that's actually what's happening at the molecular level, is it is kind of a listable bond.
Mm-hmm.
Yes.
So
it will be just more ugly to write down in the general
no,
case.
I know that. So I'm saying the question is then, if this is the canonical form If this listable bond is the canonical form, now the question is, how do we write some shorthand that allows you to specify that more easily? Okay. And essentially what you're saying is that what you typically want is, is very much like a span, a start, an end, a step for each one of them, right? For the I's and for the J's.
Yep.
Yes.
So it seems to me this can be the canonical form, which if you're generating this programmatically might be the thing you generate. Thinking about this. But this, unfortunately, is a transposed version of that. That is, that's the start A, the end I, the step I, and that. So then it's a transposed version that will be a start J here, etc. It would be nice to know what extract really does with spans. Well, that would be my suggestion, is those two possibilities. And I do favor allowing this one because I think it's useful to have something which is easily programmatically generatable. Comments?
But in this case, you could just as easily generate the bonds one by one.
You mean a list of bonds?
Yes,
I see.
It's only a minor additional hassle.
Okay, fair point. But look, if that's the concept of what the thing is representing, I mean, your point is why use that syntax for something you can generate easily another way?
Exactly. You just have n more times the word bond, otherwise it's the same.
Is there precedent in the field to use the shorthand, specifying a range of residue positions and a second range of residue positions? I'm assuming that's the origin of trying to use span.
I don't know.
We did that just naturally, but don't be prejudiced by the way we went on. I don't think that there's uniform consensus on how to do it externally.
Okay.
All right. We're going to run out of time here, so I just want to scan forward here. A comment from Richard on live stream about BioNetGen, which apparently is a language for specifying biochemical simulations. I do not know about it. Anybody here know about it? Has a domain-specific pattern calculus, Richard says.
Interesting. I'll look into it.
Okay. Okay. Next up. All right. So let me just understand the general structure of this. Oh my gosh, we got a lot of stuff to go over here. We're going to have another meeting. Well, this looks lovely. Let's do a quick scan here. Okay. Not going into as much detail.
But for now, you're fine with the specification of the spans, then we can go ahead.
I think so.
Okay.
I think so.
Okay.
I mean, okay.
And you're also fine with the mixed strand or hybrid. So then we can implement
hybrid strand seems fine.
Yeah, hybrid.
Okay.
What is this? Oh, this is some flattenability, some of hybrid strands.
I had one comment about that. If it does flatten like that, then you can't have a starter hybrid strand and then append to it programmatically.
I had the same comment. But I do see the value of this. I mean, we could always, in the worst case, let normal do this.
Or you have to start, if you want to iteratively build one up, you'd have to start with two of them, two elements to it.
I think we're talking about, these hybrid strands are already a sophisticated thing. And this auto melting of one hybrid strand into another seems like a very obscure thing.
It's basically one replacement rule if people wanted to do it.
Yeah. I mean, I don't think, I don't know why we're supporting this particularly right now. It seems like we don't know much about hybrid strands to begin with, and supporting this when we might, I mean, maybe there's some giant area of technology that's going to develop along these lines where we're going to want to annotate it differently. By the way, 4D on live stream is suggesting an operator form of bond, where you can say bond of quotes hydrogen and then span 1, span 2.
I like this when you can basically get what you wanted, have the bond at it, and then you have a nice short form of it by mapping it over.
Right. I mean, it might canonicalize to something, the other form, but having an operator form of bond seems sensible. Well, maybe is it possible? Wait a minute. Doesn't bond? No. What does it default to? That may not be possible because doesn't bond with a single argument default to a single bond?
It does.
So we're toast there. Can't work. I mean, unless we do something special for the string.
I was going to say we could do something special for the strings.
Think about it. Not sure. Let's scan forward here.
There's just a couple of new sub-values.
I just want to look forward at what's happening here. Collections of sequences.
Now kind of comes something new, basically. That's kind of a different thing now.
Oh my gosh, what's this?
That's now basically putting the two things from the beginning, the hydrogen bonds and multiple sequences together. So we have two compounds or hybrids, and they connect to each other, but only through hydrogen, not through primary bonds.
And what the heck are these things now? What are those?
So
we need more indices, kind of.
Yeah, first sequence, second motif, second position.
What is a motif? A motif is part of this hybrid strand?
Right. Anything that's kind of all one color here. The motif is, the first motif is ATCG.
Well, you didn't tell me this when we were talking about these other indexings before. And that's why you care about the flattenability of hybrid strands.
That's right.
Yes.
Because otherwise you're indexing into a structure here, which is basically, instead of a sort of a tensor rank, you're in a hybrid, a certain hybrid rank, so to speak.
I mean, we could just not support it. Kind of saying, if you want such a composite one, then composite yourself. You can't have nesting.
I just think this is, look, I want to know, is this an actual active area of people building molecules this way? Is this something people really do a lot?
It's definitely niche, but like the vaccines and stuff that you guys are taking for COVID, it's all the nucleic acid stuff that's blowing up right now. So I have like easily over a half a dozen startups working on this type of thing. And I know a lot of big pharma companies doing this type of thing too, but it is definitely niche within that scientific community.
Okay.
It's a blowing up area right now because of everything that happened with the vaccines.
Well, it's going to keep going then, because, that whole idea of delivering sort of, custom RNA that people were doing for cancer therapy has just been accelerated by a decade or something.
Oh, most definitely.
So, it's going to keep going. So we care about this. Okay, let's just look.
And this is also where multi-strand proteins would fit.
What is
that's a much more senior field that's been around for a very long time.
Yeah.
What's an example of a multi-strand protein?
Isn't hemoglobin one?
Keratin would be a multi-strand where each of the strands are connected by multiple disulfide bonds.
Sometimes you call that quaternary structure in the peptide world.
Yeah.
The protein world.
Okay, right. I've heard of that. Okay, so wait a minute. So that is a case where using the same hybrid strand idea or using a different, no, that's for a single sequence that's for something which is in a one-dimensional sequence. But the thing you're referring to is two strands next to each other, so to speak, being connected. Is that true?
Right. Yes.
Which has their own indexing nightmare.
Oh,
Yes.
These will be consistent because we can use, we can just say that a single motif just always starts at 1 and use the same scheme. There's no conflict between the two when we're going in sequence collections.
Okay, what is a sequence collection?
That's what we're looking at now, these collections of sequences that are bonded together. So we have multiple composite strands or multiple.
Is that a standard name for such things? We don't have to name them because all we're doing is looking at nested biosequences. We don't have to name the construct other than in documentation, is what you're saying. It's just a nested biosequence. Right. And then the question is, how is the thing knitted together? So, I mean, this type of question shows up. I mean, this is also related to the ports question for graphs and so on. That is, and for neural nets and so on. I mean, that is right now, you are doing everything by numbers. It is not self-evident that you wouldn't want, maybe, I don't know. Do you want a named port somewhere, as in a named position, as opposed to just numerical positions?
That would be cool.
That's useful.
Yeah, it's, I think, in the section that John has closed because it's not ready yet. But of course, we want to annotate the whole strands anyway. So this would fall into this world.
Oh boy. So the
strand,
which was just a series of characters, is going to need annotations.
Yeah, heavily.
So right. So you can imagine moving to a data structure that could allow arbitrary interlinkages that wasn't just a sequence of monomers, that could be built upon graph and could put arbitrary annotations on the vertices and arbitrary types of edges.
I mean, look, in the end, we are defining a graph. And I suspect one of the nasty things is you'll want to annotate spans. And that's going to be ugly.
Yeah. That's for sure, we'll need that. Coding sequences and all the rest.
Richard is commenting about a thing called Porgy, that apparently does port graph rewriting. Okay, interesting. We should look it up. Thank you.
I mean, we don't have to come up with the ultimate solution for everything because the fact that we are still in the linear world does simplify quite a few things here.
As opposed to what? The circular world? Or
no, some arbitrary branched looped.
Right, but I mean, generally, people attempt to do that. I mean, smiles, for example, or the generalizations of smiles attempt to kind of describe, have some sort of pseudo-linear specification of something which might have all kinds of extra linkages in it. And in the end, you just have to give a graph.
Yep, right. In the end, I mean, you need to have something that internally is represented as a graph with fast lookups of annotations and fast, programmatic access to those annotations.
Okay, so let me just understand. I mean, one of the questions here is, for example, in neural nets, we have net chain and we have net graph. A net chain is for the simple case where you just have, I mean, the fact is, right, I mean, and the question here is, what we don't want to do is to have a sort of slippery slope where we're getting more and more and more complicated, bells and whistles on top of a linear chain thing, realizing that actually the interesting cases are going to just be graphs, and we might as well, bite the bullet and just use graphs, and then have various utilities that sort of mass produce kind of, graphs with certain structure, having the base thing be a graph rather than the base thing be something with an ornate kind of a bizarre, unknown elsewhere syntax. And it worries me a lot that you're talking about annotations, because that's going to mean if you have span annotations, I don't see how that can possibly work with part numbers. Unless what you do is you say, just like the bonds are referring to spans, so somehow there can be an annotation that separately refers to a span. But that's not how we've done annotations in other kinds of structures.
It's similar to how audio does annotations, I think, right? I mean, so audio does annotations much differently than graph. When so much so that I don't fully understand when I look at two examples. But so I think audio, when you annotate an audio object, you are specifically annotating a region in it.
Yes, you are. I thought those were decently unified, but maybe not.
Well, I mean, it seems different to me because I tend to think in terms of specific vertices and yeah.
Right. Right. Well, I understand that. I mean, I understand. But so if I look up annotation,
yeah. I think you want to look up annotate.
Or even audio annotate.
What is this doing? What the heck is that? A region of interest and values. A list of regions. A region of interest and values. I see. So that's an after the fact annotation. That's not a wrapped annotation. By which I mean, one thing you could imagine is you have a list and you put a symbolic wrapper around a part of it that represents an annotation, which is what you do inside graph, for example, for individual edges and things like this. But here, what this is saying, this is an after the fact thing where you come in and say, I want this region of interest in the audio to be annotated with this value. Does that make sense?
Yeah.
Yes.
I mean, I feel like modular the fact that internally sound is discretized. There's also the difference between something continuous and discrete. Like in the discrete case, you can annotate every single of the finitely many things. In a continuous case, you need a different machinery.
I understand. Richard is commenting, seems like a job for labeled hyperedges. You know, one day we are going to have to introduce hypergraphs. I have used hypergraphs now so much in the last couple of years, and I have, you know, unfortunately there are many different kinds of hypergraphs, which doesn't help. Between ordered ones, non-ordered ones, et cetera, et cetera, et cetera. It's a more complicated story than with graphs, where sort of the directed versus undirected graph cases are, you know, they're not too hard to understand the relationship. Okay, this is lovely. So do we have a way of, I mean, did we make this kind of, is this using secondary structure computing software to figure out what shape this will be?
This is all our internal graph functionality.
We've got functions in Emerald that do folding and pairing as a thing. It'll compute.
Okay, but so I mean, is this a representation of what that RNA strand would actually look like? Oh, that's a DNA strand. So,
Absolutely.
Yeah. No, this is pure, basically graph layout. This does not take any physical interaction into account.
Right. Unfortunately, this meeting really should have been scheduled for significantly longer. This is a complicated area with lots of complicated decisions to make. And I need to go to something different.
But at least with the beginning part, you are okay. We go ahead and really implement.
I think so. I think so. I mean, but I'm a little concerned about this whole annotation, indexing, etc. thing. I just think we need a nice, principled way of approaching the whole thing. And we haven't really. I mean, Brian, has Emerald figured out some sort of systematic way of doing this, or do you think you have a good design pattern for this?
I would say no, because it's what we do anyway is people manipulate it as the pictographic form anyway. We actually box form the whole thing up, and we go the direction just like we do with Molecule, where there's like drawing tools. Use your mouse to make it. Okay. So we haven't focused too much on the underlying wrap. You guys are doing a much better job than we are of saying, this is what the one-dimensional representation should look like.
Fair enough. I mean, I think we're imagining programmatic chemistry as opposed to point-and-click chemistry, which may be completely unrealistic because I don't know what.
No, it's better from a functional perspective because we end up writing functions and then we have to deal with the headache that is our representation when we're in the weeds of those functions, like the thing that generates the foldings, right? That's a real function in simulate folding is a function in Emerald, right?
Right. No, I mean, I think, yeah, well, I'm hoping to understand this stuff a lot more when I'm as you know, I'm trying to use some ideas from our physics project and particularly these multi-way system concepts and things to understand some kind of way to approach chemical reaction networks. More about that some other time. I need to go, and sorry.
It was very useful. Thank you.
Yeah, a lot of nice stuff here, and a lot of interesting comments on our live stream. Thank you for that. And Richard is making one more comment here. Rather than spans, one may use a hyperedge. Also beats metagraphs, which allow edge-edge relations. Wow, I'm not familiar with metagraphs. That's an interesting concept. Edge-edge relations. That sounds like higher category theory of kind of you know, morphisms between morphisms and things. Interesting. Okay, all right, I gotta go. See you guys later.
Yeah,
thanks
thanks.
a lot.